Hello. In this section of the Arduino lessons, we will implement a counter project with a 7-segment display. In the application, the right button will perform the increment operation, while the left button will handle the decrement operation of the counter. In our previous lesson, we explained the concept of using a 7-segment display and created a simple application. Now, we will design a circuit with the same setup to control a counter using forward and backward buttons, but with two different code structures in two separate videos. Let's examine the circuit setup and implement the first method. When we examine the 7-segment display, we see that it has a common cathode structure. Therefore, we need to make connections of the lower and upper middle pins to the ground line on the breadboard. After that, we establish connections to digital pins starting from LED identified as A. LED A is connected to digital pin 2 and B is connected to digital pin 3. On the lower side, C is connected to pin 4, D is connected to pin 5, and E is connected to pin 6. Again, at the top, we have connected LED F to pin 7 and LED G to pin 8, thus connecting all 7 LEDs of the 7-segment display to digital pins. We are leaving the decimal point LED unconnected. We do not connect to the dot point since we won't be needing it in this example. Two buttons are used in the circuit. The button on the left will decrease the counter, while the button on the right will increase it. We are applying a 5-volt voltage to the lower left pins of both buttons through the breadboard. We had already connected the Arduino's 5-volt line to the positive rail of our breadboard. We placed 10 kilo-ohm resistors between the lower right legs of the buttons and the ground line. Arduino pins are connected to the input from the opposite direction of the applied voltage to the buttons. The left button is connected to pin 9, while the right button is connected to pin 10. We connect 220 ohm resistors to the middle pins of the 7-segment display. We're using the same resistors for the other LEDs to protect them from damage. We may not require the 7 resistors for the LEDs in the physical setup, but it is crucial to connect resistors to the middle pins. Let's proceed to analyze the code. Initially, we declare the variables related to the digital pins for the LED connections from A to G on the 7-segment display. We define variables of type integer, starting with A equals 2 and continuing up to G equals 8. Then we assign the pins connected to the buttons to variables. The variable named button right has a value of 10, while the variable named button left has a value of 9. The counter is defined as an integer variable with an initial value of 0. In this variable, we will store the digits to be displayed on the 7-segment display. Let's take a look at the setup section code in Arduino, where codes run only once when power is turned on. We come across a for loop here. We'll analyze the nearby code block to understand it. We must declare that digital pins 2 to 8, represented by variables from A to G, will function as outputs. This can be accomplished by using the pin mode command. Each of the 7 LEDs on the 7-segment display needs to be defined, which means 7 lines of code. Using a for loop for such repetitive tasks reduces the command lines and provides an advantage to the programmer when modifications are needed later in the program. For integer I equals 2 means start I index from 2. I is less than 9 means loop while I is less than 9. And I plus plus means increment I by 1 at a time. In each loop, we define the pin corresponding to the variable as an output using pin mode. So, the loop will first define pin 2 as an output, then continue defining pins sequentially up to pin 8. This way, we will achieve our task using a 2-line for loop instead of 7 command lines. Furthermore, we must add 2 more pin mode statements for the forward and backward buttons. However, we will define these pins as inputs since we will be sending the button press information to Arduino from an external source. We will make these button inputs using pins 9 and 10, represented by the button right and button left variables. We could have defined these pin modes with a for loop, but there's no need to design a for loop for just 2 lines of code. We'll move on to the loop block in Arduino, where code that continuously repeats itself as long as there is power. First, we check if the button on the right is pressed. If pin 10, connected to the right button, equals 1 meaning high, or the button is pressed, then we increment the counter by 1. We apply a 5-volt voltage to the left leg of the button. When the button is pressed, this 5-volt voltage reaches the digital pins through the button. In this case, the 5-volt voltage applied to the right button is applied to digital pin 10 when the button is pressed, and if the button is pressed, we increase the counter by 1. Initially, the counter was 0, and the moment the button is pressed, it will become 1. Similarly, we read the status of the left button using the digital read function. The left button is connected to digital pin 9. If the left button is pressed and a value of 1 is read, we then decrease the counter by 1. Thanks to these two if blocks, we have enabled the buttons to fulfill their functions. If the counter reaches a value greater than 9, we cannot display it on a single-digit 7-segment display. In this case, we need to reset the counter to 0. In other words, when the counter is at 9 and the right button is pressed again, the counter value will become 10. However, since we cannot display 10 on a single-digit display, we reset the counter at that moment. Similarly, if the counter is decremented using the left button to a value below 0, such as -1 or 2, we then set the counter value to 9. Afterward, we will ensure that the number corresponding to the value of the counter is displayed on a 7-segment display. For this, we will utilize a switch key control structure. With the switch statement, we compare the value of the counter variable enclosed within the parentheses. Subsequently, within the curly braces, case 0 meaning if the value of the counter is equal to 0 is placed. In the case that the value of the counter is 0, we will make sure that the value of 0 is shown on the 7-segment display. For this, we assign a high value to all pins except the 8th pin represented by the G variable, ensuring these LEDs light up. We set the G LED to low, thus forming the number 0. Every case statement must be concluded with a break and a semicolon. In the case of 1, the B and C LEDs will be set to high, and the other LEDs will be set to low. Likewise, for every number up to 9, the corresponding LEDs should be activated to make the 7-segment display show the numbers correctly. A visual will be shared at the end of the video to clearly show all digit codes displayed on the 7-segment display. After the final break statement in the switch case structure, we close the curly braces. To ensure stable operation of the program, we create a 250 millisecond delay and then terminate the program by closing the curly braces of the loop. Let's hide the code section now and then examine the simulation's operation. Every time we press the button on the right, the value on the 7-segment display increases by 1. When we exceed 9, it loops back to 0, allowing the increase to continue in this manner. The left button decreases the value. When it drops below 0, it resumes counting from 9. In our next lesson, we will create the same program using a 2-dimensional array. Now, we'll review the entire code for this program. Have a nice day.